Today I want to talk a little bit about differential equations. Remember that this week I'm really just reviewing stuff that you've seen more or less in your first calculus course. A differential equation is just a very simple thing. All a differential equation means is an equation involving a derivative and so what I'm going to try to do is give you a crash course in working with differential equations. So maybe let's start with the easiest differential equation of all. So f prime of x equals 0. Yeah, that's a differential equation because f prime of x, that's a derivative. And what you want to do is solve that differential equation. So you want to work out what f of x is, given that it satisfies that equation f prime of x equals 0. So I'm going to try to be just intuitive. I'm not trying to rigorously prove anything. So I don't know, what's f of 0? F of 0 is some number, let's call it c. And what that differential equation tells you is that the slope of that graph everywhere is 0. So the tangent line everywhere, in particular the tangent line at c, is horizontal. You move along a bit, the tangent line's horizontal tangent everywhere. And, you know, your kind of intuition tells you that you can sort of piece together all that local information, those horizontal tangent lines, and you reckon intuitively that the function must just be a constant function, so that the graph is just a horizontal line. So the slope is 0. Remember, derivative is slope everywhere. Of course, you don't know what that c is because you can always slide that horizontal line up or down. It doesn't change the slope, but it changes that y-intercept. So in solving that differential equation, there's some unknown kind of vertical slide, this constant c, that differential equation doesn't tell you anything about. I mean, starting from this equation, if you differentiate both sides, when you differentiate f of x, you get f prime of x. And no matter what value of c, whenever you differentiate the constant c, you always get 0. So you see that you can't resolve the ambiguity of that constant c. So this is typical when you're solving a differential equation. There's always some unknown constants that come in. This, by the way, would be called the general solution. And if you knew a little bit more, if you knew what f of 0 was, for example, then you could resolve that ambiguity of that constant in the general solution, and you would get what is called a particular solution of the differential equation, given that extra piece of information. That's usually called initial conditions or boundary conditions. So this is rather a trivial differential equation, so you might not think much of it here. So we kind of didn't prove this rigorously. We kind of had an intuitive idea that should be what's going on. If the slope everywhere is 0, you ought to be able to patch all those little local bits of information about the slope to see that your function has to be horizontal. The formal proof of this is actually a true statement. It uses something called the mean value theorem, which I'm sure you would have seen in your first course in calculus, and hopefully it was also explained how using the mean value theorem you can prove this fact that we've just observed, but I'm not going to go into that here. I'm trying to give you an intuitive feeling for what's going on. That's in keeping with the early days of calculus in the 17th century when formal proofs were not the vogue, and I think this is the right way for us to proceed in this course. So here's a slight variation of what we did. If you know that you've got two functions, f and g, and I told you that f prime equals g prime, what can you say about f and g? So the idea for this is what you do is you let h of x, the third function, be the difference, f of x minus g of x. Then the derivative of h of x is the derivative of f of x minus the derivative of g of x. And because f prime equals g prime, f prime minus g prime is 0. So this new function h, its derivative is 0. So by the previous example, you get that h of x is some constant. So that tells you that f of x minus g of x is c. And rearranging, you get that f of x is g of x plus c. So in terms of the graphs of these functions, we know very little about them. But if this was f of x, then what this is saying is that g of x is parallel to f of x. So that the difference everywhere between the y values of these two graphs, everywhere it's c. It's saying that f and g are parallel graphs. So this leads us to the next idea. So I'm going to use the following notation. And the notation looks crazy at this point. And it'll only be in the next lecture when I start explaining a little bit more about integration, how integration is calculating areas and summing things up, that this notation will make any sense. But for now, this is just some notation that I'm going to use, a shorthand, if you like. I'm going to use this notation. So this, I've put on the left there the integral sign. Integral f of x dx is going to be a shorthand for an antiderivative of f of x. So by that I mean some particular function of x whose derivative with respect to x is the f of x inside that notation. So let's underline that. This is the word I'm going to use, an antiderivative of f of x. Another word that you could call this, it's also known as an indefinite integral. And I might use that word sometimes, and that's certainly a word that you'll hear. But at this point, I haven't said anything about what integration is in any way, so I don't want to use the name indefinite integral for this thing. I'm simply going to call it an antiderivative of f of x, some function whose derivative with respect to x is the f of x inside that symbols. Okay, so this dx there, that's telling you it's an antiderivative with respect to the variable x. So it's some function of x, which when you d by dx gets you back to the f of x inside that notation. So let's see, here's an example, I don't know, just of using this notation. The integral of, what shall I do? Integral of x squared dx. So this is meant to be an antiderivative of x squared, some function of x whose derivative is x squared. And, well, we could try x cubed. When you differentiate x cubed, power down the front one off the power, using the power rule, you get 3x squared. So if I were to divide by 3, I'd get 3 times the third x squared, which would be x squared, right? So there we go. An antiderivative of x squared is x cubed over 3. And many people would write plus c here, but where c is a constant, I don't bother writing this. I never really saw the point. So when I'm writing these indefinite integrals, these antiderivatives, I usually won't bother writing the plus c. It always seems a little bit redundant to keep writing that thing. But let's look up here. What we just showed is that if you have two functions f and g with the same derivative. In other words, if you have two antiderivatives of the same function, those two antiderivatives are equal up to a constant. So what is important to realize is that this antiderivative is only defined unique up to adding a constant. So I'm not going to bother writing the plus c whenever I write integral x squared dx. I'll just, my favorite antiderivative of that is x cubed over 3. Another one would be x cubed over 3 plus 57. All antiderivatives would be x cubed over 3 plus a constant, where that constant could be anything, but I won't bother writing plus c. I'll just remember that if I'm in a situation that I've got two antiderivatives of the same function, all I know is that those two antiderivatives are equal up to adding a constant to one of them. Okay, good. So that's just a little kind of crazy notation at this point. I'm not going into detail about integration today. I'm talking about differential equations. And so this cheap and dirty notation that I've given you, integral f of x dx, short for an antiderivative of f of x, is all the language I need to talk about differential equations. But as I said, next time I'll start talking about definite integrals and integrals that calculate area, and we'll make that connection, and then this notation will start to make a bit more sense. Okay, but let's maybe do a couple of examples. So maybe something kind of really important that we should definitely know. So I just integrated x squared. So let's just do x to the n. So this, remember, what I want is an antiderivative of x to the n. So n here actually could be any real number. So we're after a function whose derivative with respect to x is x to the n. Okay, so, well, let me see. I feel like I want to try adding 1 to the power, because antiderivative, it's sort of the inverse process of differentiating. And you know the power rule for differentiating, power down the front, 1 off the power. So if we want to get x to the n, we should be adding 1 to the power. When you differentiate back again, you get power down the front 1. Oh, I need to divide by n plus 1. So what I just did here is the inverse power rule, because antiderivative, this thing we're trying to find, it's the opposite of differentiation. And to differentiate is power down the front, 1 off the power. The opposite rule, I need to do the inverse operations in the opposite order. So it's add 1 to the power. And then divide by the new power. And so that's called the inverse power rule. That's the rule for finding an antiderivative of x to the n. And it's all very well unless n is minus 1. If that real number power n there is minus 1, then that new power, n plus 1, is 0, and you can't divide by 0. So if n equals minus 1, this answer is nonsense, and you need something else. But actually, we know an antiderivative. So when n is minus 1, what is x to the n? It's x to the power minus 1, which is 1 over x. And we know a function whose derivative is 1 over x. It's called natural log. Derivative of natural log x is 1 over x. You can actually do a little bit better. And sometimes you do this and sometimes you don't bother. It depends on what particular problem that you're solving here. The thing is that the domain of natural log x is the interval 0, infinity, so only positive values of x. But you can also consider the function ln minus x with domain minus infinity 0, so anything that's negative excluding 0, and the derivative of ln minus x, so I can calculate this using the chain rule. The derivative of natural log is 1 over, evaluated at the inside, and then you've got a times by the derivative of the inside function minus x, and the derivative of minus x is minus 1. And look, I've got a minus and another minus, so this is just 1 over x again. So actually, this function, ln minus x, is also an antiderivative of the function 1 over x. So the one I wrote there, ln x, that differentiates to 1 over x with domain 0 infinity. And this guy, ln minus x, it differentiates to 1 over x with domain minus infinity 0. So you can put these two ideas a little bit together. So you actually should write the following, because it gives you a better answer with a bigger domain, which may be useful depending on the problem you're solving. So an antiderivative of x to the n, it's add 1 to the power, divide by the new power if n is not minus 1. And to write both of these functions together, ln x if x is positive, ln minus x if x is negative, you write ln absolute value x if n equals minus 1. So this guy, it has domain all real numbers except 0. And so that's kind of the most general best answer you could do. Of course, you weren't worried about 0, because when n is minus 1, this function is 1 over x, and x equals 0 is not in the domain of that function. So we were totally good throwing away 0, but it wasn't clear whether we should throw away the negative x's, and so writing it like this, natural log absolute value x, gives you a kind of a more general answer that covers more x's. Okay, so that's just this cheap and dirty notation for an antiderivative of a function. So this is an example coming from the inverse power rule, except when n is minus 1, when we need natural log, an antiderivative of x to the n. That's kind of very useful basic fact about anti-differentiation. Okay, great. So now I think I'm ready to go back to differential equations. So let's switch a little bit to using Leibniz notation and think about two differential equations. So these are going to be two examples of very simple first-order differential equations. It's the first time I've used that phrase, first order. First order differential equation is a differential equation involving just first derivatives. And in a little while I'll start showing you some second order differential equations with second derivatives. That's something we haven't talked about at all yet. So I'm going to give you just these two examples. dy by dx is constant times x, and the second example I'm going to do is dy by dx is constant times y. So here, k is some given constant, given at the beginning. So let me see. So let's just have a little bit of an aside before I tackle these two examples. I seem to have jumped ahead of myself just a tiny bit. And I just want to think momentarily, what is an antiderivative of, let's see, do we know what an antiderivative of x is? Yeah, we know that. That's x squared over 2. Or what's an antiderivative of y? Well, all that's happened is I'm using the letter y instead of the letter x. That dy means we're talking about antiderivative with respect to y. That would be y squared over 2. What about an antiderivative of something more complicated, like I'm going to give you u dy by dx. Okay, so that maybe I'm making a bit of a mess here. Let's tidy that up a bit before I start writing. So what's going on here? I'm looking for an antiderivative with respect to the variable x. So I'm looking for some function of x, which when you d by dx it, gives you the stuff inside. So in here, it's sort of implicit in this Leibniz notation that u and y are both functions of x. So here I've got the function u, and then I've got the derivative of y, dy by dx, and then the product of those two functions of x. So that's some function of x, and I'm asking for an antiderivative of that function. So I want some new function of x whose derivative with respect to x is u times dy by dx, and I want to say what that is. Let's call it v. Right, so v is just defined to be an antiderivative of u dy by dx. So what we know about v is that when I differentiate v with respect to x, it's u dy by dx. Okay, so I know a little bit about v. If I times both sides by dx by dy, I get, what do I get? I get dx dy, dv dx on the left, and I get u dy dx, dx dy on the right. But now I can use the chain rule. Remember, the chain rule is just like these were really fractions, even though they're not, and you can cancel the dx's, and you get left with dv by dy on the left-hand side. And what happens on the right-hand side, you can cancel the dx's, and you get left with dy by dy. That's what the derivative of y with respect to y, which is just 1. So you get u left on the right-hand side. These two guys just cancel out completely, and they just become 1. So we're just left with the u on that right-hand side. So this says that v is an antiderivative of u with respect to the variable y. Yeah, that's exactly what I'm saying. I'm saying v is something which, when you d by dy it, gives you u. Okay, so what's our conclusion? This v, it's actually something which, when you, is an antiderivative of u with respect to y. And I better put a plus c here, because v was an antiderivative. This was v. We've shown that v differentiates to u dy dx, and this argument that I gave shows that this thing also differentiates when you differentiate this thing with respect to x. It also gives you u dy by dx. Okay, so I've used up a little bit of room. So let me write the conclusion of what I just explained. I'm sorry, that might have been a bit confusing. I think I didn't explain it as well as I can. So we've just shown the following: an antiderivative of u dy by dx with respect to x is equal to an antiderivative of u with respect to y plus a constant. So this, you might have seen something like this. You might have called it integration by substitution or something. But at this point, I haven't got integration in place. I'm just talking about antiderivatives. This is a much easier statement. I'm just saying that an antiderivative of this function is the same as an antiderivative of this function with respect to y. And that's totally in keeping with our Leibniz notation. You see, if you just look at those dx's, it's as though those two dx's are cancelling, and you're just being left with u dy. So we'll often use this. It's often called the substitution formula for finding indefinite integrals or antiderivatives. It's really just the chain rule written in yet another way. Remember, the chain rule has so many different ways of saying it. The substitution formula, it's really just the chain rule, because, well, that was what we used when I derived it just then. Okay, so let's now go back to my two examples. Let's start off with example 1. So what I'm going to do, I guess we could just do this straight away, right? I know that y is a function whose derivative with respect to x is kx. Okay, so that's just saying that y is an antiderivative of kx. We know another antiderivative of kx by the inverse power rule. That's what kx squared over 2. So I could just go straight there, not mess around. From that I get right away that y and a half kx squared, they're both antiderivatives of the same thing, so they must be equal up to a constant. But I want to just kind of go a little bit slower and explain how I would how I would solve this in practice. All I would do is I would take the differential equation and I simply put an integral on both sides with respect to x. Let me get that right. I'm integrating both sides with respect to x. That's how I say it. You just write integral dx on both sides. Okay, so an antiderivative of the left-hand side with respect to x is equal to an antiderivative of the right-hand side with respect to x. And then now this is a place where you should put the plus c, right? This is an antiderivative, another antiderivative. Antiderivatives, you always need to put the plus c at that point. These are two different possible antiderivatives. All you know is that they're equal up to a constant. So kind of this is how I would be thinking about solving this differential equation. And in words, you just say, well, I'm going to integrate both sides with respect to x. So I get these antiderivatives being equal up to a constant. And the left-hand side, what is the left-hand side? So this might look a little bit weird. I've got just dy by dx over dx. That's exactly this expression here, where the u that I had in my more general game that I played at the bottom, when u is just 1. So by what I just said, this u is just 1. This is just integral of 1 dy. And so here on the left, I need an antiderivative of 1 with respect to y, which is just y. Here I need an antiderivative of kx with respect to x, which is a half kx squared, and then I've got the plus c in there. And so that's sort of making solving a very easy differential equation look rather complicated, but it shows you the general technique that you do when you're doing this in practice. So this is called the general solution for this original differential equation. This is the general solution. It involves this unknown constant, this constant of integration. That always happens when you're solving a first-order differential equation. Your solution always involves one constant. You would need to know a little bit more about the situation you were in. You would need to be given some additional piece of information called an initial condition or a boundary condition to resolve that unknown constant c, to work out what it was exactly, to get what would be called the particular solution given the boundary conditions. Okay, let's see if I can do the second one. So for that first one that I just did, it probably looked rather daft that I did it in such a complicated way. But for the second one, it starts becoming a little bit more useful. So what you do is you rewrite this as 1 over y dy by dx equals k. Okay, so you divide both sides by y, and then you integrate both sides with respect to x. And so you just take an antiderivative of the thing on the left with respect to x, and you take an antiderivative of the thing on the right with respect to x. And always when you take antiderivatives, those two sides are equal up to adding a constant, right? Because the left-hand side and the right-hand side, they both have the same derivatives. And then I just use my substitution formula here But now the u in my substitution formula, it needs to be u equals 1 over y. Okay, so from my substitution formula, I get antiderivative of 1 over y dy is antiderivative, the right-hand side I'm not messing with at this point. And now I need an antiderivative of 1 over y with respect to y. Well, we know that's natural log absolute value y. And on the other side, what have I got? I've got an antiderivative of k with respect to x. That would be kx plus c. Okay? So that's looking good. Let me just move this down because I don't need to take up all that space. Gives you a little time to think about what I'm talking about. Okay, great. So let's make y the subject a little better. If I do e to the power both sides, it's going to look a little bit nicer. Absolute value of y is e to the kx plus c, which is, of course, by laws of exponents, e to the c, e to the kx. So this is just some new constant, right? This c was a constant. So e to the c is just a constant. You know what? I've got absolute value of y there. Why don't I? So that's what, plus or minus y. So I could write just that y is plus or minus e to the c, e to the kx. And then what you finally do is this thing here. It's just some constant. You call it some other letter. Let's use like capital A. And so the final solution that I'm going to write is y equals a e to the kx. So a is some new constant. That's the constant of integration. This time it's sort of a multiplicative indeterminacy. This constant is multiplying. And that constant a, it can either be positive or negative, or indeed 0. Y equals 0 is a perfectly legitimate solution. Okay, so I've just kind of gone through how you solve this second differential equation. And the way I've explained it is in terms of the substitution formula. I feel like I made something quite easy, quite difficult. I'm quite good at doing that. But so let me redo those two examples again, how you actually do it in practice. So the first example was dy by dx is kx, and the second example was dy by dx is ky. So they're both really using this fact from the beginning about antiderivatives. If two antiderivatives, if you have two functions with the same derivative, those functions are equal up to a constant. And then they use this substitution formula, which is just the chain rule in disguise written in this new language of antiderivatives. So here's what you actually do. You don't go through all those complicated things that I just tried to show you, where you integrate both sides and all of that. This was even more complicated, right? And when I used this substitution formula with u equals 1 over y, what you actually do is you do this thing called separating variables. So you move all the y stuff to the left-hand side and all x stuff to the right-hand side. I mean, you let yourself do this thing which kind of isn't quite mathematically meaningful, but is justified by what I did on the previous page. It's just kind of a mnemonic for remembering what we just did and how we just used the substitution formula. So you let yourself separate that dy by dx into the dy, which you keep on the left-hand side, and the dx, which you kind of cross-multiply over to the right-hand side. Or in the second one, I want to pull all the y's to the left, so I would keep that dy there, and that y on the right I would move to being a 1 over y on the left, and the dx I'm pulling over. Right, so you separate variables, all the y's including the dy on the left-hand side, all the x's including the dx on the right-hand side, and then having separated variables, you just stick this extra integral sign at the beginning on both sides. So this is where we're taking antiderivatives, where you need to add the plus c. And so you see, in doing that, in separating variables and putting that integral, that's just sort of that operation I did on the previous page where I talked about the substitution formula, and this is just kind of the cheap trick that you have in your head to let you do this without really having to think too hard. And then you would go through and solve it, right? So an antiderivative, but this is 1 times dy. An antiderivative of 1 with respect to y is y, and this was what, a half kx squared was an antiderivative of kx with respect to x, and that was our general solution. Or this one, so this is, we're back to what we were doing here. It was natural log absolute value of y, and this was kx plus c, and the steps that we went through before, we got then that y is a e to the kx, where a is some new constant, depending on the originally chosen constant, but since it's more convenient, you should just forget the original constant and just use this capital A. So this is the general solution in the second case. So this is this key useful technique for solving these first-order differential equations by the method of separation of variables, but we need to have a little bit of caution here. Not all first-order, in fact, almost all first-order differential equations work this way. You usually can't, you simply cannot separate variables. But when you can, this method is awesome, and so there's a whole bunch of first-order differential equations where separation of variables works when you can simply integrate in this, you can solve the differential equation in the way I just showed you. Let me give you one last example. So I'm sort of just really trying to give you kind of the cheap way to see the tools that we're going to use in solving differential equations without going into too much detail about the proofs of everything. So I'm trying to be kind of informal, but I think this is enough. So let me give you one more differential equation. Let me give you like y squared plus 2xy dy by dx plus x squared equals 0. So I want you to find the general solution and then find the particular solution. So my GS, I've said that GS is general solution. PS stands for particular solution. Given that, let's give you some initial conditions, some boundary conditions, one piece of information, so that we can resolve those constants of integration that appear. And let's carry on the question, what can you say about the domain of the function y? Y, remember, y is implicitly a function of x in this particular solution. Okay, so I'm going to try and solve this differential equation. So the first thing you try is you try to take that equation and you try to rearrange it, letting yourself separate the dy and the dx, just because that's the handy trick of separation of variables. Try and rearrange it so that all the y's are on the left and all the x's are on the right. And, well, I mean, if I'd given you this quadratic, y squared plus 2xy plus x squared equals 0, and you were trying to solve that quadratic, you wouldn't be able to just move all the y's to the left and the x's to the right and solve, right? If you were solving that quadratic, you would have to do something like factor it as y plus x squared, and then square root both sides or something. This is a sort of similar issue. You simply cannot rearrange this equation to put all the y's on the left and the x's on the right. You just can't do it. But if you just kind of look at it a little bit, you might come up with the trick. And so here's the trick, which takes a little bit of luck and a little bit of intuition and a little bit of guesswork. It's to see that on the left-hand side, I can rewrite that left-hand side as the derivative with respect to x of xy squared. So this is our equation. So this took a little bit of good luck that I happened to notice this trick. I happened to make this observation because, I mean, what is the derivative of xy squared? Well, it's a product, so I can d by dx it using the product rule. It's the derivative of the first derivative of x with respect to x is 1 times the second, that's the y squared, plus the first times the derivative of the second. And the derivative of y squared with respect to x, well, you know how to do this. This is a chain rule. Derivative of y squared with respect to x is the derivative of y squared with respect to y, but then you have to multiply by dy by dx. So that's what? The derivative of y squared with respect to y is 2y, and then there's a dy by dx. You're hopefully following. So when you differentiate this thing, the derivative of the first times the second is this term, and then we've got the first times the derivative of the second, and the derivative of the second is this 2y dy by dx. So this whole expression, when you use the product rule to differentiate, it's exactly what we had in the original equation. But it took a little bit of insight, a little bit of experience to recognize that you could rewrite that y squared plus 2xy dy by dx as the derivative of this product, xy squared. So this is part of the game. Differentiating is always easy, but anti-differentiating, which we're going to call integration, is a little bit of a harder process. It's sort of it needs more experience, more kind of, because the product rule is easy going forwards, but hard going backwards. The chain rule is easy going forwards, but hard going backwards. That's the game. What's going on? Okay, so now we've written our equation in a different way, and now we can separate variables. So I haven't got all the y's on the left. I'm treating this xy squared as some new variable. I mean, I could name it something else like u, and then this would be du. Right? I've done a separation of variables, but not between y and x, between this new crazy variable u, which is xy squared. And then you can put integral on both sides. There we go. So these are equal up to a constant. And so now what have I got to do? I've got to find an antiderivative. Remember, there's secretly a 1 in here. I've got to find an antiderivative of this. The variable is now called xy squared. So xy squared, I could call it u. This would look less crazy. The derivative of u with respect to u is that 1 that's secretly sitting there. And on the right, what have I got? I've got x squared. I've got to add 1 to the power, divide by the new power. And now I've found my general solution. Let's try and rearrange a little bit to make y the subject. So y squared is, what have I got to do? I've got to divide by x, so that's minus x squared over 3. I like to just rearrange a little bit because I like my minuses in the middle. I've got that c, and I'm dividing by x. So this, for this constant c, this right here, this is the general solution with that constant. And then let's carry on. So that was the general solution. Now we want to find the particular solution given that y is 0 when x is 1. So all you now do is we're trying to find c, so you just plug in y equals 0, x equals 1. So the left-hand side is 0. The right-hand side is c minus a third. So that tells us that this constant, which was unknown in the general solution, has now been worked out given that initial condition, that extra boundary condition, that constant c must be a third. So actually y squared is a third. What have I got? 1 over x minus x squared. I could square root both sides. Y is square root of a third, 1 over x minus x squared. And now we can just finish off the last statement. What can you say about the domain of the function in this particular solution? So you see, this solution, it doesn't make sense for all x's. There's a restriction on the x's where this makes sense, because we've got a square root here. We want this term inside to be positive. So we really need that 1 over x is bigger than x squared, and we're told that x equals 1 is in the domain. So actually the domain for this function, if you think about this a little bit, 0 is a problem, right? You can't have 0 in the domain because 1 over 0 doesn't make sense. We want x equals 1 to be in the domain, and if x is bigger than 1, well then that's smaller than 1, take away something, so that would be negative. So the domain actually is just this, it's the open on the left, closed on the right interval, 0, 1. That kind of is a good example that demonstrates when you solve a differential equation, the solution might not be defined everywhere for every possible x. You get some restricted domain, and indeed the particular solution will often, the boundary conditions will often tell you where the domain is. One last thing should be said. In even writing the differential equation like this, look, we've got dy by dx appearing. So it's kind of implicit that this function has to be differentiable on the domain that you're looking at. Because, well, for a function to be for dy by dx to make sense, your function has to be differentiable. And probably you remember the word continuous. You remember the differentiable functions are in particular continuous functions. So this is why that's the limit of my domain. I can't go to negative x's because already at x equals 0 it's not defined. Okay, so hopefully that was a reasonable example to just kind of get you into this game of solving differential equations by separation of variables. The above are first order differential equations, and I've talked about separation of variables as our main technique for solving first order differential equations. I think that'll get us through all of the differential equations that we see when we're doing applications of this stuff. But I want to just talk a little bit about second order differential equations. Which involve second derivatives. So we've got a function f of x. The first derivative we've talked about. We haven't talked about the second derivative. Well, but you can take the first derivative and then you can differentiate again. Maybe I should write it here. So you can take the first derivative and then you can differentiate that again, right? The first derivative is a function. You can differentiate it again. Or in Leibnizian notation, that would be y. That's dy by dx. This would be the second derivative is called d2y by dx squared, which looks a little bit weird, but it's not so weird when you realize that what you're doing is you're starting at y, you're d by dxing it to get the first derivative, and then you're d by dxing again to get the second derivative. And if you kind of keep into this Leibniz spirit where you want these symbols to kind of obey the normal sorts of rules of algebra, you would write that as d2, it's d times d, dx squared, which would be dx times dx, right? And then there's the y. So that's sort of justifying that rather weird looking notation. It's quite handy. Okay, so fantastic. Let's see if we can come up with an example. Let's give you maybe a really simple example. d2y by dx squared equals k, some given constant. Okay, so this is maybe the easiest possible second order differential equation. So all this is saying is that the derivative of dy by dx is k. So what's dy by dx? Well, it's an antiderivative of k. So dy by dx must be kx plus some constant. Okay, so now we know dy by dx. So what's y? Well, y, when you differentiate it, gives you dy by dx. So y must be an antiderivative of this function on the right-hand side, which I can do. I can find an antiderivative of that using the inverse power rule. I get a half kx squared plus cx, and then I can have any more constant. So c and d are these constants of integration. And because this was a second order differential equation, it's typical that when you find the general solution, there are two unknown constants involved in your solution. So now you would need, so this would be the general solution. You need two initial conditions, two boundary conditions to find the particular solution, if that was what you were trying to do. Okay, so that's a very simple second order differential equation.